All right, folks, welcome back. At the end of the previous video, I said that I would take this conical tank problem and do it standalone as a standalone video. So here you go. And we're going to look at that problem with the following in mind. I have given you a procedure. Hopefully you picked that up on your way into class. And this procedure works for every single related rates problem that we'll ever do in this course. So I took a lot of time making sure that this procedure was thorough and detailed. I'm going to go through it step by step for you on this problem, this conical tank problem. After that, it's up to you to use it as you see fit. Okay, the first step in the procedure says identify all given quantities and quantities to be determined. Make a sketch and label the quantities. So let's go ahead and take a look at the problem itself. Conical tank, vertex down, is 6 feet tall with a radius of 4 feet. The tank is draining at a rate of 5 cubic feet per minute. When the water level in the tank is 2 feet, at what rate is the depth of water changing? All right, so let's go ahead and draw a sketch of what we're dealing with here and then find all the quantities we're given and the quantities we need to determine. Okay, there's our conical tank. I'm not going to lie, that's a pretty good sketch for you there. Some of the ones that I see students do, not so good. Okay, so we have a conical tank, vertex down. It's 6 feet tall, so let's make sure we label the height of this. It is got a radius of 4 feet, so let's go ahead and make sure we show that in our picture. The radius is 4 feet. The tank is draining at a rate of 5 cubic feet per minute, so we actually have water coming out the bottom of this tank. Water's draining out the bottom. Show our water line in there. And then we've got water that's draining out at 5 cubic feet per minute. And that quantity right there is dV/dt. That's the rate of change of water volume in the tank. And we're going to call that -5. The reason why I'm calling it negative is because the tank is draining. The water's draining out. You'll notice here that I haven't tagged this with any units. I'm going to be a little sloppy with my units as I go through the problem. At the end of the problem, I'll go back and make sure that they all work out. Just so you know, I'm going to keep all units in terms of feet and minutes. And then at the end, I'll check to make sure that our units make sense. Okay, when the water level in the tank is 2 feet, so this is a height of water. And when that water level is 2 feet, we are interested in finding this rate. What rate is the depth of water changing? Well, that is dH/dt. We have to find dH/dt at h equals 2. That's the quantity we have to determine. So let's go back up and check our procedure. We've taken care of step 1. Identify all given quantities and quantities to be determined. Make a sketch and label the quantities. So we're done with that. Now step 2 is probably the most challenging part. Write an equation involving the variables whose rates of change either are given or are to be determined. Well, we have one rate of change that's given, and that's dV/dt. And we have one rate to be determined, that's dH/dt. Okay, so we need to write an equation involving just the variables whose rates of change are either given or to be determined. This bullet right here applies to this problem. If you're given dV/dt and asked to find dH/dt, you should only have the variables v and h in your equation. All right, so let's go ahead and take a look at the formula for the volume of a conical tank. The formula for the volume of a cone is 1/3 pi r squared h. Most formulas that you need on the AP exam will be given to you, but there are some you should know, like you should know how to find the area of a triangle. You should probably know how to find the area of a circle. The one with the cone here, they would probably give that to you. I'm guessing they might give that to you and they won't necessarily expect you to have that memorized. After all, this course is about calculus, not about memorizing volume formulas. Okay. Let's now take a look at what we have to do here. So we have to rewrite this equation just in terms of v and h. So that means we need to get that r out of here. We have to find some relationship in the picture or in the geometry of this of the application where we're able to get rid of r. And I want to highlight here, I'm going to go ahead and add some detail to this sketch. So there's my height, and then my radius is right here. Okay, so you'll notice we have, I don't want to get too geometric on here. There are a number of ways to relate h and r, but one way to do that is to look at similar triangles. Okay, we have a big triangle here, and we have a little triangle here, and they share an angle down here, and they also share a right angle. So there's a ratio there that's going to be consistent. The ratio of the height of water to the radius of the water is going to be 6/4, and that ratio will be constant for whatever amount of water we have in the tank. Okay, so this relationship here between h and r, I need to get r out of my volume equation, so I'm going to go ahead and solve for r right now. So if I rearrange that formula, I get r equals 2/3 h, and I'm now going to substitute that in to my volume equation. Okay, so I made that substitution. I am now going to do as much simplifying as I can on this. 2h squared, the quantity 2h squared will be 4h squared times h is 4h cubed, and then I have this pi, so it's going to be 4 pi. I have an h cubed, and then my denominator is going to be a 3 squared, which is 9 times 3, which is 27. So that is an expression for the volume in the tank as a function of the height of water in the tank. I do want to pause real quick and go back to this expression here. I don't want to trivialize this. This was not an easy thing for me to look at the picture and figure out what the relationship was between h and r. However, that's the tricky part of many of these problems, is you have to be able to find the relationship in the geometry that gets rid of the variable that's not either a rate given to you or a rate you're looking for. In this case, that was r. And there are a number of ways you could do that. Let me just give you quickly another way you could have done that. You could have said, you know what, I'm going to set up a linear equation that goes from this point to this point that expresses r as a function of h. You could have done it that way as well. I just chose to do it with similar triangles. Okay, so now I have this volume function as volume as a function of height. It's time to take a derivative. So let's go ahead and take the derivative of this whole thing with respect to time. dv dt on the left. Now I have this constant of 4 pi over 27, constant multiplier. I'm going to include that. Now I have to take the derivative of h cubed. That's going to be 3h squared times dh dt. Okay, let's go ahead and let's clean this up just a little bit. dv dt equals, let's see, I have a 4 pi times 3, all divided by 27. Well, there's a factor in here of 3 that I could cancel this. So that now becomes 4 pi h squared over 9 times dh dt. Now I kind of wrote it separate like this because dh dt is the quantity that I would like to find. So I'm going to rewrite this equation and solve for dh dt. dh dt equals 9 times dv dt divided by 4 pi h squared. So that is the rate of change of the height with respect to time in terms of the rate of change of volume with respect to time and the height at a given instant. So let's go ahead and actually solve for the quantity they asked for. We were asked for dh dt when the height equals 2 feet. So I'm now going to plug in all the quantities I know. Remember, dv dt is -5. And because it's an application problem, I'm going to give my answer as an approximate decimal. So if I plug that expression in my calculator, I'm going to get -0.895 and that's going to be in cubic feet per minute. And there's my final answer. Let's just add some context to that. I want to make sure you understand what that value represents. When H equals 2, height of water in the tank is decreasing by 0.895 feet per minute. So that adds some context to what that number represents. Just a couple other comments here. I mentioned earlier that I was going to be a little sloppy with my units, but I would come back and make sure that everything worked out correctly in the end. If I look at my equation here for dH dt, I have this constant 9 times dV dt divided by 4 pi times the quantity h squared. So the only thing with units there are the things that are highlighted. Let's just make sure those units work out. dV dt was in cubic feet per minute, and h is in feet. If I square that, I have square feet. And when you divide cubic feet per minute by square feet, you end up with feet per minute. And that deserves a big green check because the units worked out. Folks, that's it for example 3, the conical tank problem, a classic related rates problem in calculus. There are 3 more problems to do on the back side of the notes page. So we're going to shut this video down and then see if we can't do those 3 examples in another video.